I am P. Mabu Hussain, Assistant Professor of EEE in Institute of Aeronautical Engineering, Hyderabad. Today, in this video, we are going to discuss about the flux linkages of one conductor in a group of conductors and the inductance of composite conductor line. So, let us see the flux linkages of one conductor in a group of conductors. So, here we are going to take a group of conductors. Okay, so n parallel round conductors which are carrying the current, right? We are considering a group of n parallel conductors which are carrying the currents I1, I2, I3 up to In, and the sum of all the currents will be equal to 0. So that means I1 plus I2 plus I3 plus and so on plus In will be equal to 0. So we are considering a group of conductors, right? We are considering a group of conductors, and current flowing the each conductor is represented with I1, I2, I3 up to In, and these conductors currents are such that the sum of all the currents will be equal to 0. Now you consider a point P, so which is far away from the conductors. At here you consider a point P. So now the distances from this point P to all conductors you can represent it with D1, D2, Di and Dn. Right? Here in a group of parallel conductors, we are represented the conductors with the numbers 1, 2, 3, I, J up to N you have. Right? So each conductor is carrying a certain current, and the distance of each conductor from a remote point P will be D1, D2, Di up to Dn. Now you have to develop the flux linkages of one conductor in a group of conductors. Now if you consider the ith conductor here, so if you consider the ith conductor, so then the flux linkages of ith conductor, so due to current flowing in that conductor, right? So we are considering the current flowing through that conductor I itself, and we are going to develop the flux linkages expression, right? Now as you know, so the distance from this conductor I to the remote point P will be Di here. So now the flux linkages of ith conductor, so due to current flowing in its own, so that means you are representing this as lambda is the flux linkages of I represents the ith conductor due to current flowing in the ith conductor itself, right? So lambda II represents this. Okay, so lambda II is the flux linkage of ith conductor due to current flowing in the same ith conductor. So this value will be equal to 2 into 10 power minus 7, and current flowing through the conductor is II ln Di by R I dash. Okay, so this Di is the distance from this ith conductor to remote point P by R dash, Ri dash you have to take the radius of that particular conductor I dash. This Ri dash value will be equal to 0.7788 times the Ri. Okay, so now you have to develop the flux linkages of the same ith conductor due to current flowing in the jth conductor. Okay, so now consider the current flowing in the jth conductor, which is Ij. Now you have to develop the flux linkages equation in conductor I due to the current flowing in the jth conductor, right? So this expression can be written as lambda Ij. So lambda Ij in the sense, lambda means flux linkages, I here, so flux linkages of ith conductor due to current flowing in jth conductor. So this value is equal to 2 into 10 power minus 7, and current flowing through the jth conductor is Ij ln distance from jth conductor to remote point P, so which is Dj by the distance between ith and jth conductors. So this distance you have to consider, so which is Dij. Okay, so this is the flux linkages of ith conductor, so due to current flowing in the jth conductor. So in similar way, so by using this expression, you can develop the flux linkages of ith conductor due to current flowing in the first conductor, which is di1. So this value will be equal to 2 into 10 power minus 7 into I1 ln. So this distance from first conductor to remote location point P. So this will be d. So d 1 by distance from this first conductor to jth conductor, which is di1. So in similar way, you can develop the flux linkages of ith conductor due to current flowing the second conductor. So which is lambda I2. So which will be equal to 2 into 10 power minus 7 into, so current flowing in the second conductor we are considering. So this is I2 ln. So distance from second conductor to the remote location will be d2. So by, so distance from ith conductor to second conductor. So like this, you can write the flux linkages of ith conductor due to current flowing in each and every conductor. So up to n. So din will be equal to 2 into 10 power minus 7 in ln dn by din. Okay. So these are the flux linkages of one conductor I due to current flowing in all other conductors. So now if you write the total flux linkages of ith conductor, so then the total flux linkages of ith conductor, which is represented as lambda I. So this value will be equal to, so flux linkages of conductor I due to current flowing in the first conductor plus flux linkages of ith conductor due to current flowing in the second conductor plus, so flux linkages of ith conductor due to current flowing in the same conductor II. So plus and so on, flux linkage of ith conductor due to current flowing in the nth conductor. Okay. So while developing the flux linkage for one conductor, you have to consider the current flowing in the all the conductor. So then you have to develop the total flux linkages. Okay. So this is the total flux linkages equation. Okay. So now you already know that this lambda I1. So what is the lambda I1? So lambda I1 is the 2 into 10 power minus 7 ln d1 by di1. So into I1, sorry. So here also you will get I1. So plus, so d8 in the sense 2 into 10 power minus 7 I2 ln d2 by di2 plus on so on. So if you say the current flowing the same conductor, so then this will be 2 into 10 power minus 7 ln di by dii. Okay, plus on so on. So due to current flowing the nth conductor, the flux linkages will be 2 into 10 power minus 7 in. So here I you have to consider, right? In ln d n by d in. So this is the, so flux linkages of ith conductor due to different currents. Okay. Now from this expression you can write 2 into 10 power minus 7 as common. Okay, you are taking 2 into 10 power minus 7 as common. So then you have here I1 into ln d1 by di1 plus here I2 into ln d2 by di2 plus on so on ia into ln di by dii. So now this dii you can write it as ri dash. Okay, so the self distance you can consider to be dii. So that value will be equal to ri dash. So here you are writing in place of dii you are writing di dash plus on so on for nth current flowing in the nth conductor. So that constant is in into ln dn by din you will get. Okay. Now after getting this equation, so from the first term, so which is ln d by di1, right? So ln d by di1, this can be written as, so the first term is I1 into ln d1 by di1. This can be written as I1 ln 1 by di1 plus I1 ln d1. Okay. So like this you can expand the each term here. Okay. So each term in this equation you have to expand in this form. Okay. So that you will get lambda is equal to, so 2 into 10 power minus 7 into, So the first term I1 into ln 1 plus di1. So 1 by di1 plus from this I2 into ln 1 by di2 plus and so on ia into ln 1 by ri dash plus and so on in ln 1 by din plus. So the second term we are repeating here, right, from the same from each term, right, I1 into ln d1 plus I2 into ln d2 plus I2 ia into ln di plus in into ln dn. Okay. So right, now you got this expression here. Okay, now you know that the sum of all the currents in all the conductors will be equal to 0. Okay, so this is equal to 0. So from this, if you write the in value, right, so in value will be equal to minus of I1 plus I2 plus up to in minus 1 conductor. Okay, so you will get the value of in will be equal to minus of I1 plus I2 plus and so on up to in minus 1. Now here this in value we are going to substitute here. Okay, so in the second term here, so in value if you are going to substitute here, so then what you will get here in the second term, in place of this here you will get minus of I1 into ln dn plus I2 into ln dn plus I3 into ln dn plus on in minus 1 into ln dn. Like that you will get. So in place of this you will get this expression, so which is having the negative sign. Okay, now if you take this I1 ln d1, I1 ln dn. Okay, so you take these two terms, here this term and here this term. So then if you take I1 as common, so then you will be having ln d1 minus ln dn. So this can be written as I1 ln d1 by dn. Okay, similarly if you take the second term here and here, so then this can be written as I2 ln d2 by dn. So like that you can write for all the terms. So then this lambda I expression will become this equation. Lambda I is equal to 2 into 10 power minus 7 or 2 into 10 power minus 7, and this expression is you have to take it as it is, right? This expression there is no change, so you take it as it is. So I1 ln 1 by di1 plus I2 ln 1 by di2 plus and so on plus ia into ln 1 by ri dash plus and so on plus in ln d ln 1 by din. So plus, now here the second term, so the second term after substituting the value of in, so it is going to I1 by ln d1 by dn, right, I1 into ln d1 by dn plus I2 into ln d2 by dn plus and so on ia into ln di by dn plus and so on plus in minus 1 into ln dn minus 1 by dn. So this is the flux linkages in ith conductor due to the current flowing in the all other conductors. Now here so in order to account for the total flux linkages of the conductor I, so this is small I, right, conductor I. So let us assume that point P, what we are assuming here, so it is residing at infinity. This point P we are moving it to infinity. In such a case, you can say that the value of d1 will be equal to d2, which will be equal to d3, which will be equal to dn. So those all the distances will be approximately equal. Why? Because when you move this point to infinity, from infinity distance to d1, infinity distance to d2, all the distances will be almost approximately same. So d1 will be approximately equal to d2, approximately equal to dn also. So from this expression, if you see the second term in the lambda I here, so d1 by dn, so d1 by dn, it will become it will become 1. Why? Because so this d1 and dn, so when the point P is at infinity, so this d1 is approximately equal to dn, so this value will get approximately equal to 1. So here in the second term, all the values, so d2 by dn, di by dn, dn minus 1 by dn, all the values will become equal to 1 here. Okay, if you consider the point P is at infinity. Okay, so now the ln1 value, as you know, so this value will be equal to 0. So this total second term is going to be vanished. That the total second term value will be 0 only. Okay, so the flux linkages of conductor I, so due to current flowing in the all other conductors, which is lambda I, will be equal to 2 into 10 power minus 7 on the first term only, so which is I1 into ln 1 by di1 plus I2 into ln 1 by di2 plus and so on, plus Ia into ln 1 by dii. So d in place of dii, you can even write it as di dash. Okay, so plus and so on, plus in into ln 1 by din. Okay, so this is the expression for the total flux linkages of one conductor, here ith conductor, right? Total flux linkages of ith conductor due to current flowing in all other conductors. Okay, so you have to remember this equation. Okay, right. So here while deriving this equation, so flux linkage of one conductor in a group of conductor, we consider the n number of conductors, right? So now if that n number is reduced to 2 or 3, how the flux linkages equation you will get, let us see. Okay, so the flux linkages of one conductor in a two conductors group. Okay, so we are taking only two conductors, 1 and 2 here, right? So now we are going to develop the flux linkages equation of one conductor in this two group conductors. Okay, so then how we can write? So the generalized equation is this one, so which we derived in the previous slide. Okay, so lambda I is the flux linkage of either conductor in a group of n number of conductors. So this value is 2 into 10 power minus 7 into I1 into ln 1 by di1 plus I2 into ln 1 by di2 plus up to in into ln 1 by din. Okay, now if there are only two conductors, so which is like a single phase system, so then for the flux linkage of first conductor, if you want to write, how you can write? So flux linkage of first conductor, so this will be equal to, so flux linkage of first conductor due to current flowing in the same conductor, which is lambda 1 plus flux linkage of first conductor due to current flowing in the second conductor. Okay, so this is the total flux linkages. Okay, so now, so this value if you write 2 into 10 power minus 7 ln, so d1 by d11 plus 2 into 10 power minus 7 ln d2 by d12 you will get. Okay, so now from this expression you can write 2 into 10 power minus 7 ln 1 by d11 plus, so this is I1. Right, see if there are two conductors in a single phase system, so the flux linkage of first conductor due to current flowing the both the conductors, you can write, so by using this generalized equation itself. Okay, so the lambda 1, so which is the flux linkage of first conductor due to current flowing the both the conductors will be it will be equal to 2 into 10 power minus 7 into I1 into ln 1 by d11 plus I2 into ln 1 by d12. Okay, similarly if you write for second conductor, so the flux linkage of second conductor due to current flowing in the both conductors will be lambda 2, which will be equal to 2 into 10 power minus 7 into I1 ln 1 by d12 plus I2 ln 1 by d22, so which is in Weber turns per meter. Okay, similarly you can extend this to a group of three conductors also. Okay, so flux linkage of one conductor in a group of three conductors, here it is like a three phase system, right? So let us take three conductors are A, B, C here, and distance between A and B is represented with D12, and distance between A and C is represented as D31, and distance between B and C is represented with D23 here. Okay, so now you are going to write the flux linkage of first conductor A So due to current flowing in all three conductors. Okay. Then the flux linkage of first conductor A, lambda A will be equal to 2 into 10 power minus 7 into current flowing through the first conductor, which is IA, so into ln 1 by DAA. So 1 by DAA you can write, which is will be same as RA whole dash. Okay, 1 by RA dash plus current flowing through the second conductor. If you consider, the flux linkages will be IB into ln 1 by the distance from the first conductor to second conductor, so which is D12, plus if you consider the current flowing in the third conductor, which is IC, so then flux linkages will be IC into ln 1 by distance from first conductor to C, which is D31. So this is the flux linkage of conductor A due to current flowing in all the conductors. In similar way, if you write the flux linkage of conductor B, so then the flux linkage of conductor B will be equal to 2 into 10 power minus 7 into, if you consider the first current IA, so then IA into ln 1 by, so here 1 by D, distance between A and B you have to write, D12 you have to write here. So D12 you have to write here. So plus current flowing in the second conductor is IB into 1 by D22 you have to write. So then plus IC into ln 1 by D B to C distance is 2, 3. So here you will get 2, 3. Okay. So this expression, if you write, you will get lambda B is equal to 2 into 10 power minus 7 ln 1 by D12. So D1 IA into ln 1 by D12 plus IB into ln 1 by RB dash plus IC into ln 1 by D23 you will get. Okay. So like this you can write for the conductor C also. Okay. So you have to remember this generalized equation. So flux linkage of either conductor in a group of n conductors. So then you can write the flux linkage of one conductor in any group of conductors. Okay. Then, so let us see what is a stranded conductor or a composite conductor. As you know, in a transmission line system, we are not going to use solid conductors. Okay, we are not going to use solid conductors like this. Okay, so why? Because when you use the solid conductors, there may be more losses will be there due to skin effect, and even maybe having the corona loss. Okay, so because of that reason, instead of using solid conductors, generally we use the stranded conductors. Okay, so these stranded conductors, in the sense, so instead of using one single conductor, we will use the strands of conductors which are arranged in like a layers. Okay, if you see this conductor here, so this is a stranded conductor. Okay, so now in this stranded conductor, the conductors are arranged in layers form. Okay, so the first layer will be having only one conductor. Okay, second layer will be having some conductor, third layer will be having some more conductor, fourth layer will be having some more conductor, like that. Okay, and the total number of strands in a standard conductor, if you want, so that value will be calculated by using the expression n is equal to 3x square minus 3x plus 1. Here x represents the number of layers here. Okay, so if you are having only one layer, so one layer, then so this value will be 3 minus 3 plus 1, which is equal to 1. So only one conductor will be there in a single layer conductor. So if there are two layers are there, so then, so how many conductors are there? So 3 into 2 square minus 3 into 2 plus 1. So which will be equal to 12 minus 6 plus 1. So which is 7 conductors. Okay. So in a two layer conductor, you will be having 7 conductors. So in the first layer, you will be having one single conductor, and on the top of that, you will be having 6 conductors. Okay. So if you are having a 3 layer conductor, so then x will be 3. So then number of conductors will be 3 into 3 square minus 3 into 3 plus 1. So 3 into 3 is a 9 minus 9 plus 1. So it will be So 27 minus 9 plus 1. So now here what will get? 19 conductors. Okay. So 19 conductors will be there. So that means out of 19, first layer will be having 1 conductor, second layer will be having 6 conductors, and the remaining conductors will be there on the third layer. Okay. So 12 or 13. 13 I think so. Okay. So 12 only. So like that. Okay. So depending upon the number of layers, you will be having number of strands. Okay. So always remember that single central strand will be treated as the first layer, and it will be having only 1 conductor. Now, if you want the overall diameter of the conductor, so if there are any number of layers, then if you want to calculate the total diameter or overall diameter of the stranded conductor, so this will be equal to 2x minus 1 into d. Here x is the number of layers, and small d is the diameter of each strand. Okay, if you know the diameter of each strand, which is small d, and the total number of layers inside a stranded conductor, so then the overall diameter you can find by using this expression. Okay, so now here if you see the figure, so it is the cross-sectional view of ACSR conductor, so which is having 7 steel conductor strands and 24 aluminum strands. 2 layers if you see, so 2 layers are having steel strands and the remaining are aluminum strands. So that means in a stranded conductors, the strands are made up of different materials. Okay, the strands, the 2 layers, top 2 layers are made up with aluminum strands, and inside layers are made up with steel strands. Okay, so because of that reason, this is stranded conductor, you can also call it as a composite conductor. So composite in the sense, it will be having different materials inside the conductor. Okay. So composite conductor and standard conductor, both are the same almost. Okay, if you are having the strands with only one material, then you may not call it as composite conductor. But if you are having 2 materials in a standard conductor, that will become a composite conductor. So generally, so we will use the ACSR conductors in the transmission line system, in which you will be having aluminum strands as well as the steel strands. That steel strands will be used for increasing the mechanical strength to the conductor. So because of that reason, the conductors are called the composite conductors, as we are having 2 materials. So now let us calculate the inductance of composite conductor line. Okay, let us take a single phase transmission line in which you will be having 2 phases. Okay, 2 phases will be there. One phase is phase A, another phase is phase B. Okay, so now here we are going to assume each phase is having a composite conductor, right? So that means you will be having number of strands here in phase A with different materials, you can say. Okay, so let us assume that composite conductor A will be having the conductors numbered from 1 to n, and composite conductor B, so which is phase B, is having the conductors numbered as 1 dash, 2 dash up to m. Okay, so this is a single phase line, so which is consisting of 2 composite conductors A and B. So A is having n parallel conductors, or you can call them as a subconductors, right? So n parallel subconductors, and B is having the m parallel subconductors. Okay, so now let us assume that current flowing in composite conductor is A is I, and current flowing through the conductor B will be minus I. So why? Because in a single phase system, one conductor acts as a forward path, and another conductor will act as a reverse path, right? So current in conductor A is I, so then current in conductor B will be minus I. Now here we are assuming that current distribution in the each composite conductor will be uniform. Okay, so that means the current will be equally divided among the subconductors of each composite conductor. So that means if the current flowing in the conductor A is total current is I, now this total current I will be divided into all the subconductors in a conductor A. So as you are having n number of conductors here in the composite conductor A, so the current flowing in each conductor will be In by n. So sorry, I by n. Okay, so conductor 1 carries subconductor 1 carries the current I by n. So 2 also I by n. So n also I by n. So the current is equally divided. Okay, so now in conductor B, you are having m number of subconductors. Now, so the current flowing to the conductor B is the return current, which is minus I. So if this minus I is divided among all the conductors equally, so then current flowing in the each subconductor in a conductor B will be minus I by m. So in each conductor, the current flowing will be minus I by m only. Okay. So now we have to develop the flux linkage equation for conductor A as well as conductor B. Right. So the flux linkages of ith subconductor here. Okay. Ith subconductor in composite conductor A will be given as lambda I. So which will be equal to 2 into 10 power minus 7 into I by n. So here we are considering the subconductor I in composite conductor A. Now we are developing the flux linkages equation for this conductor I. Okay. So in this group, in the total group you have to take. Okay. So this will be equal to, so 2 into 10 power minus 7 into, you have to consider current flowing the all subconductors while writing the flux linkages for ith conductor along with that same current also. So if you consider the current flowing in the first conductor, so then that will be I by n, right? So this will be I by n into ln 1 by distance from ith conductor to first conductor, which is di1. Okay. So plus, if you consider the second conductor, so this will be I by n into ln 1 by di2 plus on so on, like this, like that you can write up to n conductors. Okay. So if you write for n conductors, so that value will be I by n into ln 1 by din you will get. Okay. So this is one term. Now at the same time, you have to consider the subconductors in conductor B also. If you consider the first subconductor I1 dash here, the current flowing through this is minus I by m. So for that, if you can write it as minus I by m ln 1 by distance from this conductor to ith conductor. This will be di into 1 dash plus, so minus I by m ln 1 by di2 dash if you consider the second conductor. Like that you can write up to m subconductor. So which is minus I by m ln 1 by dim. Okay. So from this, so if you observe, in all the terms you are having I by n as common. So here in the second term you are having minus I by m as a common. So you take those two terms common. So then you can write the flux linkage of ith subconductor in composite conductor A as lambda I is equal to 2 into 10 power minus 7. If you take I by n common, so I by n into ln 1 by di1 plus ln 1 by di2 plus on so on, plus if you write for the same conductor I, so you will get ln 1 by dii plus on so on, plus if you write for nth conductor ln 1 by din. Okay. So then for the second term you will be having minus 2 into 10 power minus 7 I by m, you can take it common. So then ln 1 by di1 dash plus 1 by di2 dash plus and so on, plus ln 1 by dim dash you will get. So this is the total flux linkages of subconductor I in composite conductor A due to current flowing in all subconductors. Okay. Right. Now in the both the terms you are having 2 into 10 power minus 7 into I as common. You can take it outside. Okay. From this 2 into 10 power minus 7 into I, you can take it outside. Then so here in this term you will be having 1 by n. Right. So this total term if you see here, so this total term you can write it as 1 by n into ln 1 by di1 plus into di2 into di3 and so on up to din. Okay. Similarly here if you take this as common, so then 1 by m minus 1 by m into ln 1 by d I1 dash d I2 dash and so on d I m you will be having. Okay, so now for this expression you can write it as 2 into 10 power minus 7 into I. So now this 1 by 1 by n you can take it the power of this term. Okay, so then you will get ln 1 by d I1 d I2 and so on d in whole to the power of 1 by n by, sorry, not by, so this value minus ln 1 by d I1 dash plus d I2 dash and so on d in dash whole to the power of 1 by m you will get. Okay, now this will be looking like log a minus log b. So the final expression if you write, you will get this equation. So 2 into 10 power minus 7 I into ln this total term. So d I1 dash plus d I2 dash plus d I3 dash plus up to d im whole to the power of 1 by m by d I1 plus d I2 plus and so on d II plus and so on d in whole to the power of 1 by n. Okay, so this is the flux linkage of ith conductor, ith subconductor in a conductor A. Okay, now if you want to find out the inductance, so once you know the flux linkages, so you can calculate the inductance, right? So inductance of ith conductor will be equal to flux linkage of ith conductor by current flowing in the ith conductor. Current flowing in the ith conductor is I by n here. So that we are going to write here. So the inductance of subconductor I, so will be written as Li. So this value is equal to lambda I by 1 by n. Now, so lambda I value is this one. So this total value by, so I by n if you take. So then this I and this I will get cancelled. So that you will get 2 into 10 power minus 7 into this n into ln d I1 dash d I2 dash up to d im whole to the power of 1 by m by d I1 d I2 up to d in whole to the power of 1 by n. So this is in Henries per meter. This is the inductance of subconductor I in a composite conductor A. So now if you find the average inductance of any one subconductor, so here the ith conductor in the group of conductors, so then in such a case this average inductance you can write it as, so sum of all the inductances, so L1 plus L2 plus L3 plus and so on Ln. So all the inductances in subconductors by total conductors n. So this is the average inductance of one subconductor in a composite conductor A. So similarly, in conductor A, you are having a total number of n subconductors which are electrically connected in parallel. So the inductance here you can write it as La. So this La will be equal to average inductance by total number of subconductors in the composite conductor A. So the L average value is this one, L1 plus L2 plus and so on plus Ln. So by n. So then if you substitute here this value, so then the inductance of composite conductor A you will get is will be equal to L1 plus L2 plus and so on Ln by n square you will get. Okay, right. So how you get L1, how you get L2, how you get Ln? Simply here in place of I, if you substitute 1, you will get the L1. If you substitute I is equal to 2, you will get L2. So like that you can write the inductance for all n subconductors in a composite conductor A. Okay, so here you substitute all the values of L1, L2 up to Ln in this equation. So then the final equation for inductance of subconductor A or inductance of composite conductor A, you can write it as 2 into 10 power minus 7 ln d1 dash d1 dash d1 2 dash up to d1m. Next, if you take the second conductor d21 dash d22 dash up to d2m plus on dn1 dash dn2 dash up to dnm whole to the power of 1 by mn you will get, and in denominator you will get d11 d12 up to d1n. If you take the second conductor d21 d22 up to d2n, and if you take the last conductor dn1, dn2 up to dnn whole to the power of 1 by n square you will get. Okay, so here how you get this equation. So to get this equation, so here in this equation LA, you have to substitute all the inductance values L1, L2, L3 up to Ln. How you will get the value of L1? So this L1 you simply get from this equation. So by substituting I is equal to 1. So the value of L1 will be equal to 2 into 10 to the power of minus 7 ln d1 1 dash d2 d1 2 dash like that up to d1 m whole to the power of 1 by m by d1 1 d1 2 onto d1 n whole to the power of 1 by n. So this is L1. Okay, so like that you can write L2 also. L2 is equal to 2 into 10 power minus 7 ln d21 dash d22 dash up to d2m whole to the power of 1 by m by d21 d22 up to d2n whole to the power of 1 by n. So like this you can write for up to Ln. So Ln will be 2 into 10 to the power of minus 7 ln dn1 dn2 up to dnm whole to the power of 1 by m by dn1 dn2 up to dnm whole to the power of 1 by m. So in the numerator term you will be having dash. So 1 dash 2 dash like that. So here also 1 dash 2 dash. So in denominator you have to consider the 1 2 3 like that. Okay, so now you are going to sum all these L1 plus L2 plus L3 up to Ln and divide that value by n square. Okay, so if you do the sum of all these, what you will get? So 2 into 10 power minus 7 it will be the common. Okay, so 2 into 10 power minus 7 will be common and you take this n square as it is here. Okay, so then sum of all these. So this will be log a plus log b plus log c like that. So log a b c you will get. So then ln this total term d11 dash d12 dash up to d1m whole to the power of 1 by m. So like that. So all the terms d21 dash d22 dash up to d2m whole to the power of 1 by m. So like that up to m terms you have to write by. So d11 d12 d13 up to d1n whole to the power of 1 by n. So if you take d21 d22 up to d2n whole to the power of 1 by n up to m terms you have to write like that. Okay, so now if you take this 1 by n square, it will be the power of this, then you will get this. Okay, so this total term is initially having m. Okay, so the final equation here you will get will be 2 into 10 power minus 7 ln this total value. Okay, so now the numerator term. So this numerator term you will call it as a mutual GMD. So which is represented with dm, and denominator term you can call it as a self GMD. So which is ds for a particular conductor A. Okay, so then the inductance equation will be written as LA is equal to 2 into 10 power minus 7 ln dm by dSA, which is in henries per meter. So now if you convert this into logarithmic term, so, then you will get LA value will be equal to 0.461 into log dm by dSA millihenries per kilometer. Okay, you can use any one of these two equations. So first will be in henries per meter, second will be in millihenries per kilometer. In similar way, you can write the inductance equation for conductor sub B also. So this will be equal to 2 into 10 to the power of minus 7 ln dm by dsb you will get. Okay, so what is this dm and dsb? So dm is the mutual GMD and dSA is the self GMD of conductor A, and dsb here is the self GMD of conductor B. So what is this? So here the numerator of the argument in the logarithmic term, if you observe from this, the numerator term here, this value if you observe, so that value will be having the mutual geometric mean distance, so between conductor A and conductor B, so and it will be updated as dm here. Okay, so that dm represents the all mutual distances or mutual geometric mean distance, so between the conductor A and B. Okay, and this geometric mean distance will be having mnth root of mn terms. Okay, so here if you see, so this is 1 by mn, so which is nothing but mnth root of mn terms will be there here. Okay, so mn number of terms will be there. So which are the product of all possible mutual distances from n subconductor of conductor A to m subconductors of conductor B. Okay, if you observe the denominator, so this denominator here, so that denominator of that term will represent the self geometric mean distance. Okay, self geometric mean distance of conductor A, so which is nothing but it is the n squared root of n square product terms, so which is nothing but n sets of n product terms, and each set consisting of the term dii, so that di value you can write it as r dash, so for that particular subconductor, and then n minus 1 distances from that of the other subconductors in the same conductor. Okay, so this is how you can develop the equation for inductance of a composite conductor in a single phase line. So let us calculate the self GMD and mutual GMD of single phase line by considering two subconductors only. Okay, so here we developed the inductance equation by considering the n subconductors in composite conductor A and m conductors in composite conductor B here. So instead of taking n number and m number here, so in composite conductor A I am taking two conductors, so composite conductor B also I am taking two subconductors, and we are developing the self GMD and mutual GMD, right? So now if you want to write the mutual GMD, so the mutual GMD, so then how you can write, you have to take all the mutual distances. Okay, so now if you the conductors A is having two conductors 1 and 2, conductor B is having two subconductors 1 dash and 2 dash. Okay, here you have to take the product of all mutual distances, so that means if you take the for conductor 1, so 1 to 1 dash, 1 to 2 dash, this is the mutual distances, so d1 1 dash, d2 2 dash, this is one set. Okay, similarly if you take the second subconductor of conductor A, so mutual distances from conductor A to conductor B will be d21 dash, d22 dash, so you have to write another set as d21 dash, d22 dash whole to power of 1 by mn. So mn here is nothing but m is the number of subconductors in conductor A, which are here 2. So n is number of subconductors in conductor B, which are also 2. So 2 into 2 4 here. So this will be the value of dm. So dm is equal to d11 dash into d22 dash into d21 dash, d22 dash whole to the power of 1 by 4. Okay, so this is the product of all mutual distances by considering each subconductor. Okay, from conductor A to conductor B. So now DSA. So DSA is called the self GMD of conductor A here. Right. So while writing the self GMD of conductor A here, you have to consider only the conductors in conductor A only. Okay, we are writing self GMD for conductor A. So here this conductor A is having 1 and 2 conductors. Okay, now you have to write the distances between these subconductors in the same conductor A, right? So if you take the first conductor, the self distance will be d11. So then another distance is d12. If you take the second subconductor, then self distance will be d22 and the distance is d21 whole to the power of 1 by, so total number of conductors whole square you have to write. As here you are having two conductors, 2 square you will get. So this value will be d11, d12, so d21, or D22 whole to the power of 1 by 4 you will get. Okay, similarly you can write the self GMD for conductor B also. So then for this the value will be equal to which is DSB. So if you consider that 1 dash D1 dash 1 dash one product, D1 dash 2 dash, so this is one set you have to consider. If you take the second conductor D2 dash 2 dash into D2 dash into D2 dash 1 dash whole to the power of number of conductors whole square. So 1 by 2 square will be there, again 1 by 4 you will get. Okay. So like that you can determine the self GMD and mutual GMD of a single phase transmission line with 2 subconductors. Suppose if you are having the 3 subconductors also you can determine, right? So now here in phase A you are having 3 subconductors and in phase B also you are having 3 subconductors. Now the mutual GMD, how you can write? So mutual GMD is nothing but it will be having the set of products by considering all the mutual distances of one conductor to other conductor, right? So if you take the conductor A and conductor B, here the conductor A is having 3 subconductors, conductor B also having 3 subconductors. Now if you consider the first subconductor in conductor A, so from conductor A to conductor B, how many mutual distances will be there? So here this will be D11 dash, D12 dash, D13 dash. So those product you have to write D11 dash, D12 dash, D13 dash. Okay. If you consider the subconductor 1 in conductor A, the mutual distances from conductor B to subconductor 1 will be 1 dash, 2 dash, 2 3 dash. Okay. Similarly, if you take the subconductor 2 here also, so then the mutual distances will be D21 dash, D22 dash, D23 dash. So if you take the third one, D31 dash, D32 dash, D33 dash, you will get whole to the power of 1 by. So you have to 1 by, here you have to write the product Mn. So M is represents the number of conductors in conductor A, which is 3. So N is number of conductors in conductor B, which is 3 again. So the root will be 1 by 9 you will get, right? So 1 by 9. So this term you will get. Okay. So now if you write for self GMD, so self GMD in the sense you have to consider the only one conductor, either it be A or B, right? So self GMD of conductor A will be DSA. So self GMD of conductor B will be DSB here. Okay, DSA will be, you can write it as by considering the each subconductor. So if you consider the first subconductor, you write all possible distances in the same conductor, right? So D11 self distance also you have to consider D11. So then D12, D13. So if you consider the second subconductor D22, D21, D23. If you consider the third one D31, D32, D33 whole to the power of 1 by, so 1 by total number of conductors whole square you have to write. So in conductor A you will have 3 subconductors, so 3 square you will get. 3 square again it will be 9. Okay. So in conductor B also if you write self GMD, so that is represented with DSB here. So that DSB is equal to, you have to consider the conductor B subconductors 1 by 1 and you have to write the all possible distances, which are D1 dash 1 dash, D1 dash 2 dash, D1 dash 3 dash, so which is one set, then D2 dash 1 dash, D2 dash 2 dash, D2 dash 3 dash into, if you consider third one D3 dash 1 dash, D3 dash 2 dash, D3 dash 3 dash whole to the power of 1 by, so number of conductors square, again 3 square you will get. Okay. So here in DSC or DSB you are having the terms D11, D22, D33. Okay. These are the self distances. This value will be generally equal to R dash. So radius of that particular subconductor whole dash. So which is nothing but 0.7788 times the R value. Okay. So this is how you can develop the self GMD and mutual GMD expression in a single phase line which is having 2 subconductors or 3 subconductors or any number of subconductors. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.